I'll come to the Tuesday ARA seminar, and we'll have Gerald Dunne talking about mining perturbation theory. So we'll hear more about how to actually retrieve information, analytic information. Thank you.
Thanks, Anish. So I noticed we have this room booked for 2 hours. So I hope people are going to ask questions. Okay, so this is based on some work done in the last few years with Ovidiu Costin. Unfortunately, to leave but it's motivated by some problems in field theory, quantum mechanics. But I think the ideas are actually fairly general. It's really get across to everybody. I'll describe the basic idea, give you some examples that illustrate the mathematics of it, and then a few physics examples. I have an infinite number of physics examples, so we'll see how far we'll be. Please feel free to ask. So this is the problem I want to think about. It's a very common situation in application. So imagine you're trying to calculate some function, but it's a really difficult problem. And the best you can do is to calculate some number of terms in some expansion about some particular point. And that may not be the point you're interested in. So you're interested in maybe analytically continuing that information to some point, but you only have very partial information about the function. So what can you do? And what's the best thing you can do? So this is a difficult question. It hasn't been addressed much in mathematics. And it's clearly very much motivated by problems in physics. And using ideas from Resurgence, that's the reason I'm talking about here, using ideas from Resurgence, it turns out you can develop better tools, and it's actually surprising just how much better. And they call it mining perturbative data because as a physicist, you've got some finite amount of resources, and you want to get as much information, maybe non-perturbative information about a different point of expansion from that finite resource. So some inspiration from Resurgence. Resurgence suggests that expansions of a general physical function should be related as expansions about different points. And generically, these are actually not just analogs, they're real quantitative relations between expansion. So if that's true, then maybe you can use that fact somehow to develop better extrapolations and continuations from one point of expansion to another. And so the idea underlying this is to take advantage of this to develop optimal and maybe near optimal methods for what is essentially numerical analytic continuation. And one of the reasons why this isn't a completely crazy idea from dealing with physics is that one of the applications underlying this is that very often in physics, perturbative expansions are asymptotic. And I'll show you that it's best to work in the Gerald plane. Actually prove that it's much more precise to work in the Gerald plane. But then you have a problem with continuation. But in physics applications, the Gerald plane is not random. Resurgent function is endlessly continuable in the plane. So the singularities could be anywhere in general. But in physics problems, that's not what happens. It's structured. And you can take advantage of it. And I'll show you why that's the case. And the reason it has structure is because it's genuine physics. It is the non-perturbative physics. That's what this is. So the strategy is going to be to systematically probe the neighborhood of the singularities as precisely as possible. And it should be pretty clear, I hope, But if you're interested in things like connection formulas, Stokes constant, whatever, that information is lying near the singularity. So if you can probe the singularities and resolve the singularities much better, then when you take your transform back to the physical plane, you'll have a better analytic continuation. And the basic toolkit is surprisingly simple. It's conformal maps, uniformizing maps, and some variant, some type of other type methods. And the other idea coming from Resurgence is that there are actually rigorous proofs here for the class of resurgent functions. I'm not going to talk about them today. There's a couple of recent seminars that Ovidiu's given talking about certain things. I'm going to talk about the practical implementation of this. So why am I, as a quantum field theorist, interested in this? Well, there are lots of problems we don't know how to do. And I'm interested in things like extrapolating from weak coupling to strong coupling, high temperature expansions to low temperature expansions, adiabatic approximations to non-adiabatic situations, et cetera, et cetera. And the reality is that in the interesting quantum field theories, at this point, we have access to maybe 5 orders of perturbation theory. So in QED and QCD, the beta functions into 5th order perturbation theory. The electron anomalous magnetic moment went to 5th order perturbation theory. The muon anomalous magnetic moment is one of the big outstanding problems in theoretical physics at the moment. Other important field theories like scalar field theories, phi-4 and phi-cubed. There's been a lot of activity in recent years. We're now up to exact 7th order calculations in phi-4 and 4 dimensions with 11th order estimates. And through the work of Eric Panzer and Nishi Borinsky, 20th order numerically is not out of the question. There's also been significant recent progress in more symmetric field theories. Symmetric field theories are integral models. We can use other tools rather than just standard perturbation theory. And we've learned a huge amount about those field theories, about perturbation theory in general from that. This is just to say there's a lot of activity, and I think it's the right time to ask ourselves, what are we going to do with this information? All right, so I'm going to begin with just a simple example to make sure we're all on the same page, but this also captures a lot of the physics situation. So this goes back to Euler, and then of course a lot of work by Dingle. And so now I'm going to talk about the asymptotic series, but remember that since we're going to work in the parallel plane, we could just as well be talking about a convergent expansion. So imagine a factorially divergent series, here some coefficients that have some factorial growth with some power and some overall constant S. And so these 3 things in blue are the most interesting things physically. This tells you the leading exponential in non-perturbative effects. This tells you the exponent of the fluctuations around that non-perturbative effect. And this tells you something about the strength. So if you're able to extract those 3 coefficients, those 3 numbers, from your perturbative information by looking at some large order growth, you've learned something about the non-perturbative physics from the perturbative. So this is a baby version of the bigger problem. Now, let's scale B to 1, because it's not really important. We won't worry too much about the Stokes constant yet. We'll come back to that later. So if this is the actual growth, not just the leading growth, then this is just the asymptotic expansion of the incomplete general multiplied by an exponential. So alpha here is the exponent. So this guy has this asymptotic expansion, but we also know that it has this non-perturbative connection form. If you rotate minus x either that way or that way, there's a jump which is exponentially small. There's also a very simple Borel representation. It's just a simple function with one branch point cut, whose exponent is exactly this parameter. And the perturbative expansion of the Borel is just the expansion here divided by n factorial. So that's all. This is a problem that's totally under control. Okay. Now, the question is, suppose you don't know that this is the Gerald transform and you don't know that this is the actual function you're looking at. All you have is some finite number of terms in the expansion and correspondingly some finite number of terms in the Gerald transform. Yeah.
Just to be clear, that difference thing is you're analytically continuing it one way and then the other way.
It's the jump. So imagine we only have a finite number of terms in this expansion. What can we learn about the actual structure? Can we learn this connection formula? What can we get? So one of the well understood methods goes by the name of Perturbation. Because the problem is if you have a truncated Gerald transform, it's just a polynomial. So there's not a lot of information there about its singularities because it's the singularities of the transform that tell you about physics. So a simple method that's incredibly powerful but has limitations is just to make it very approximate to that truncated polynomial. And for this particular function, it turns out you can do it in closed form. It's just a ratio of Jacobi polynomials. We heard from Andy's talk last Friday, there's a very deep connection between Perturbation and orthogonal polynomials. And that's the key here. Perturbation, you can think of it in terms of these orthogonal polynomials, and then it's their asymptotics that tell you something about the behavior. So for example, this is Jacobi polynomials with index alpha minus alpha in some particular variable. We can use the uniform asymptotics of this to get some estimates. So just remember that this expansion here is at small p. That corresponds to the large x behavior in this function, out of plus infinity. But now suppose you want to extrapolate down to small x. And what you need to know is what's the large p behavior. But how do you get that from just a finite polynomial? Well, from this uniform approximation here, you can see that the behavior goes like this. And the important thing is that p scales like n squared. This is just a property of these polynomials. And what that means is that when you integrate, this means you can get your chosen level of precision down to some x value that scales like 1 over n squared. Okay? It's just a transform scaling argument. So you can start way out at x equals infinity. You can choose, say you want 1% precision. You can extrapolate down to some point, and as you vary your number of terms in the expansion, you'll be able to go further, and it scales like 1 over n squared.
In the previous slide, you had two quantities. One is f and one is b.
Yes.
So what is the relation between them? Yeah.
This is b.
Yeah, but why are you interested in b?
Because this is an asymptotic expansion. This is the Gerald transform. Familiar with Gerald?
Yeah, so that's a transformation of f.
That's one we're looking at. It's a little possible. So the Gerald transform is a regularization of the asymptotic series. It brings it under control. And now, if you can understand the singularity structure of the transform, you understand the global properties of the function. This is generated as a small p expansion, so it corresponds to large x. But now, if you want to extrapolate down to small x, you need to know something about how this thing behaves logically. Okay. Right, so that's interesting that we can go down to some point that scales like 1 over n squared. So that should dispel a common misconception, at least amongst physicists, that getting more terms in an asymptotic expansion is a waste of time. It's only true if you do the dumb thing of just truncating the expansion. If you treat the expansion carefully, and of course more information translates into more information. And here it scales like 1 over n squared. So that's quite impressive. Just a completely trivial transform gains you this 5 words. The other thing to note from this page is some result. It's a very general result of Pade. It goes back to the work of Ziegel for polynomials, but more recently, work by Stahl in the late 90s. But what Pade does is it actually creates, in the limit as n goes to infinity, it creates its own conformal map. And the reason for that is that Pade is, of course, representing this polynomial as a ratio. So the only singularities Pade can have are poles. Obvious. But if you're interested in a function that has a branch cut, in this case, then if it's just one branch cut, then Pade will just put poles along a line accumulating to the branch pole. And the density of those poles contains information about what type of branch pole is exponent, for example. But it's extremely difficult to extract that information using just the coefficients. I'll show you that it's extremely easy to do it using coefficients. But this, so what Pade does is it creates, as n goes to infinity, puts a cut there, and so it's created the domain of maximal analyticity. And this function here in blue is exactly the conformal map variable. As n goes to infinity, Pade actually generates its own conformal map. The catch is, in simple situations like this, where we're just along the line, it's no problem. But if you have singularities like that, which happens very often in physical applications, what Pade does, similar also at infinity, which is very often the case, it just makes curved arcs of poles. And what it's doing physically, this is very interesting to physicists. Of course, Pade is just an algorithm for expanding and comparing coefficients into their expressions in terms of determinants. It's just, it looks like algebra. But in fact, what it's doing, it's creating a capacitor. Think of these as electrical charges in two dimensions interacting with logarithmic potential in two dimensions. In the limit as n goes to infinity, Pade places these poles in such a location that if they become a wire, the shape of that capacitor is conductor has minimal capacity. It's actually what Pade does. This is a great discovery in the second one. Now that you know that, you can use all your physics intuition about electrostatics to understand what's going to happen in complicated cases. And to use it to develop ways to get around the defects. However, this also tells you immediately, just one more thing. Since Pade is trying to represent a branch cut by poles, it tells you that even though Pade does remarkably well away from these would-be branch cuts, it's hopeless near them. There aren't poles. It's a branch cut. So we need to do better than that.
Does that statement just about the diagonal Pade? Was that any Pade approximate by n there? Or?
So the theorems are about near diagonal.
Okay.
And again, physically, it's pretty obvious that near diagonal is the normal one, because why would you put it far from diagonal? The theorems are actually this concept of the deviation from diagonal. So strictly speaking, that's what. And I'll just to keep things simple, I'll talk about diagonal just off that. Okay, so that's good, but not great.
So another question. You said that you can discern what type of branch cut is from the density of like how do you distinguish between types?
So I don't want to go there because it's a long discussion, but roughly speaking, you convert your ratio of polynomials to a continued fraction. Coefficients of a continued fraction and studying their convergence properties, you can deduce the unfortunately not very well known fact. Trouble is that it's an incredibly inefficient. It's interesting, it's not interesting. All right, so I mentioned that Pade creates its own conformal map, but if you know that there is, or you suspect that there is in fact a branch cut, say, along here, why not map this cut plane into the unit disk? Simple conformal map to do that. And re-expand your function in terms of the new variable, in Z, re-expand in that. Now, this is well known and well used in physics, but in almost 99% of the cases, they miss the point. The point is to then do another. If you just map into the disk, it's exactly the same as doing that. But if you do both, you gain another factor of n squared. So if you do this map, then in fact, still the exact Padet polynomials are different Jacobi polynomials. The index is now 2 alpha instead of alpha. The argument is the conformal map. It's inverse. And now you can again use the asymptotics. You see that now it scales like interval. So this tells you that with exactly the same information, n coefficients, if you do this conformal map and then by day, instead of being able to extrapolate down to a point that scales like 1 over n squared, you can go like 1 over n to the 4th. If n is 10, that can be a big deal. Okay? It's just a simple scaling. I have no idea why nobody did this example. It's very instructive. But it's better than that, because now if you go near the branch point, the poles are the poles of these Jacobi polynomials, which lie in the interval -1 to 1 of the argument. But if you look at where they are in the B-plane, they're on the next sheet. So in fact, near the branch cut, this thing is essentially perfect.
So
Yep.
you go from n squared to n to the 4th, but what about the prefactors?
So we have the
But it doesn't.
yeah, and this is the dominant.
Okay, that's it.
So there are. This is the main effect. All right, so here's a plot using just a choice of the exponent -1/3. Here's the branch cut going from -1 down to -infinity, the exact function. This is what happens if you use per day. This is with 10 terms. And so you see this line of poles here trying to be a cut. And obviously, if you try to go near that cut, if you just do the conformal map and don't do the subsequent method, it's better, but you still have these unphysical oscillations. They have nothing to do with imaging. If you do both, it's essentially indistinguishable. Okay? And it's because the poles are actually on the next ribbon sheet. We'll talk much more about this. But the message here is that an incredibly simple extra step makes a big improvement. So let me show you some examples. This conformal map has another advantage, is that very often in physics applications, this leading dominant branch point is telling you about the leading non-perturbative effects. If it's a nonlinear problem, most of the problems are interested in nonlinear, these will generically repeat in intergeometry. Okay? Now, suppose you just do per day, you see a whole bunch of poles here, and how do you know that those are actual poles? They're buried under these per day poles. Now, if you study the asymptotics of these continued fraction coefficients, you can't find them. But there's an extremely simple way to do it, is that if you make the conformal map, it actually separates things because it maps them. So the leading one might get mapped to there, the next one gets mapped to there, and the next one gets mapped to there. And they're completely separate and resolved. And now you can probe them individually. And you can go explore the neighborhood of each one individually. You can actually look at local Stokes constant, structure the function here there, show you in detail later how to do that. There's this simple step that helps you resolve things that are just hidden under these.
What if like the second or the third one is still like a branch point? Do you assume that they're all the same order?
No, what I'm saying is that if you just make them just based on this one, make that conformal map, you will resolve these ones.
And those would necessarily not have coalescing sequences of holes to them.
They do, but they're outside the
Okay.
index.
Sorry, yeah.
Since it's a domain of analyticity, you have to say circles, analytic this, where are they? They're outside. Later, I'll show you a better way to do this, where you can actually go smoothly across sheets.
Yeah, when you take the Padilla approximant, usually there's some region where the poles are actually quite well captured by the Padilla approximant, and then the singularities. So there's a lot of singularities near branch points, for example. I'm just talking about the usual Padilla. So then you do this transformation, and that you do the conformal map
first.
Yeah. Yeah, but then I assume that is there some region of in the conformal variable? Is there some region where you should do the expansion? Because I assume that some.
I'll talk about that as we go.
Okay.
Okay, so here's just to show, here's a plot of the Penode-1 Futon K solution. On the left is if you just do Padilla, you see that you resolve the leading singularities be normalized to 1, but beyond that, you get this complete nonsense of random poles that are supposed to be represented in the graph. Whereas if you first do the conformal map, then you resolve 1 into some number of coefficients. So again, the conformal map does two things. It gives much better precision near the branch point and helps you resolve. So let's look at now some examples. The first one is to look at Penode-1, and it's not because we need the other one. It's because this is a function that has interesting structure in this plane, and it's very well known. Really solid analytic results that you must be able to reproduce. And so that's why we decided to study this one. And it is, of course, of great interest in physics. So here's the equation. If you haven't seen it before, just know that it's a nonlinear equation. It's easy by scaling to see that the appropriate variable is not x, but x to the 5/4. And it's known that it has these 5 sectors, anti-Stokes, Stokes, anti-Stokes lines. That's because there's an inherent 5-fold symmetry, which again is just a scaling out in the equation. This goes back more than 100 years to be true. Is that asymptotically, this is just a Weierstrass P function, but not in the variable x, it's in scale. However, in this shaded region here, this so-called Triton K solution, which was expanded at infinity in inverse powers of this 65/4, so that's way up here. In this region, it behaves completely differently. It's a meromorphic function, it has an expansion starting with a second order pole, and then subsequent expansions. Okay. So here's the clip. So this is very well known. So this is a finely tuned, completely finely tuned solution of Penode-1. Poles are only within this region, which was a conjecture of de Broglie, but it was since. So the question is, suppose you do this expansion at infinity, but you only do it to certain terms. Do those coefficients know about this? So this would be a manifestation of resurgence that perturbative expansion knows something about the expansion of the function in other regions, even though you've gone through these nonlinear Stokes transitions going from one region to the next. Is it in those coefficients Cn? And if so, how do you extract it? Of course, this is a well-known equation, so there are many ways to do this, so you can check. But the applications we're thinking of, you may not even know the equation. What can you do? All right. So we use the conformal map. This is a case where we have 2 symmetric leading branch points. They're of course repeated, but we can make the conformal map based on this doubly cut plane. So this is a very simple thing. And do the procedure. Map into the disk, re-expand, but they map back to the original. 2 lines of can't even call it code. Very, very simple. That enables you to go very close to the origin and even beyond the origin into this forward. You now have a representation that's a Borel interrepresentation of the function. You can now make a Pade in the x-plane of that thing. And you discover, and this was done with 50 terms of the expansion, it's supposed to match this form. Right? So first of all, you can find the location of the leading pole to extreme precision. And when you expand about that point, you discover that this residue, which is supposed to be 1, is close to 1, with 30 something digits. The next one should be 0 is 0. The next one should be 0 is 0. The next one, well, the next one should be 1/10 of that pole location. Well, it is to 30 something digits. The next one should be 1/6. It is. The next one is the new constant. Remember, any solution is characterized by 2 constants. And in this meromorphic form, any solution to NLA1 is characterized by the location of one of its poles and the corresponding coefficient h in the expansion of that pole. The interesting thing is you can expand around any point. It's those 2 numbers that completely characterize the solution. And then the next one should be 0. It is. The next one should be the pole squared of 300. It is. So this is a surprisingly accurate demonstration that just from these expansion coefficients, you can see an asymptotic expansion generated up here, go through these regions and turn into something completely new. The other thing you can do is that there are very precise connection formulas that relate the tree truncate solution along this line, and there's another one that relates along this line, along this line. And you can check that those are satisfied. The relation between here and here is an oscillatory behavior, fits perfectly. The relation between here and here is an exponential. That one also fits. So all of this exact non-perturbative connection form information about the solution can be generated from these expansion coefficients generated. So this is an example of what I mean of mining this information without actually knowing about this. I'm going to stress that integrability plays absolutely no role here. You can change the power of y from y squared to y cubed, same thing. It's no longer integrable, you can implement the same. Okay? Yeah.
Just to be clear, so you do all your Pade analysis in the Borel plane, and then you go back into the X plane by actually taking the Laplace transform, and then you have the data, and then you play around with that data. Oh, no, you just picked it. So that's
Yeah, and actually, this is a good point. I forgot to mention, even in the case of that incomplete gamma function, the standard Dingle type factorial power type expansion, you could have just done Pade in the X variable. Okay, it's perfectly reasonable. But the scaling there would be 1/n instead of 1/n squared. So as far as I know, this was first observed by Barry Simon in one of his papers on the anamorphic oscillator. He just noticed that if they did Pade in the Borel plane, it was together, if they're doing Pade in the physical domain. No explanation. He said, oh, this is curious. But now we see why it's true. You can really see the scale. All right. Yeah, oh, sorry.
How many coefficients did you use for this study?
Position. Good question. I think it was 50. But
Oh,
you get much higher precision in seconds.
Okay.
So this is just baby stuff. Now we get to the real one. Okay, we can do much better than this. So this is an actual theorem. So this was work with Ovidiu a couple of years ago. So now let's try to consider a general question. And so I'm just going to work in, if you like, in the Borel plane, because I don't want this just to apply to asymptotic theories. This should apply to problems like in statistical mechanics. We want to find the location of a critical temperature, work out the critical exponent. So the function you're dealing with is a convergent expansion. So you either apply it in physical domain. So imagine your function lives on some Riemann surface, which you may not know. You can map it into the unit disk, and it's Riemann theorem. And this uniformizing map can be normalized in this way, and that is unique. So the theorem is that within the class of all functions having a common Riemann surface, which roughly speaking for the purposes of this talk just means their branch points are in the same locations. You don't have to specify the exponents, just the locations. You map not using a conformal map, but using this uniformizing map of the truncated expansion. You re-expand in that variable, and it's important that you re-expand to the same order. This is subtle. You might think that if you expand to further orders, it gets better, but it actually is a sweet spot where it's optimal to expand to the same errors as you go away from it. And then you can map back to the original Riemann surface. So the difference now is using a uniformizing map rather than a conformal map. So I'll explain what that means. First of all, notice that explicit maps are known in terms of elliptic functions for the complex plane with 3 branch points. These are completely known. This is classical mathematics. And if there are symmetries, you can solve it for more singularities. You might think that's a limitation because a general problem may have many more than 3 singularities. But very often in applications, there are, say, 1, 2, or 3 dominant ones. And so implementing this just on those dominant ones leads to such a dramatic improvement that it's already interesting. However, in the process, we found the uniformizing map, the exact uniformizing map for all of the truncated solutions. It's expressed in terms of this inverse elliptic norm function as a logarithm. So that gets all of these repeated in. So it's absolutely exact uniformization. But that's because the boundary guys are switching. Real applications, we're going to have to work with just a few dominants. All right, so now I have to show you something about this map. I'm going to show you an animation in a second. So if I put 2 of the singularities at -1 and 1 and infinity, then this map is in terms of a particular function called the modular lambda function, which is expressed in terms of theta function. Don't worry about the details. What it does is it takes this doubly cut plane here, cuts from -1 to -infinity, 1 to infinity, and it maps it inside this unit disk, but it doesn't map it. A great surface. So this, oops, okay, so this maps inside here, but that's because it's just the first Riemann sheet. This region here, these regions between blue and the red, they represent the second image, and so on. So you've all seen these pictures of the repetitions of these uniformizing maps, and that way you cover the entire Riemann system. You just iterate, you fill out the whole unit disk, and you have all of the Riemann systems. Okay? This dashed black line, these dashed black lines here represent this gap between the 2 functions. And this red line here is the reflection of these lines in this line. Okay, in hyperbolic geometry. And then to get the next one, you would reflect these in here, and continue. So you've seen these pictures by MC Escher. This is how he actually collaborated with Felix Klein, generating these pictures.
Just ask, so what happens to the map if you go back to the original sheet?
Let me now switch to animation. So, screen here. Okay, so this is an animation of this. Turn around so I can see what's happening. So this point and this point are images. So I'm going to move this point around inside the disk. Okay? Remember, everything's come, this is analytic now everywhere in the disk. The first Riemann sheet is just within this blue region. So now I'm going to wander here inside the disk, and you see the point moving on the doubly cut plane. Approaching the branch cut, I'm going through the branch cut onto the next sheet. Okay, now I have three choices. I can go this way, I can go this way, and then I can go through that. So let me first go this way. What happens is I go around there and I cross the other cut. Okay. But suppose I decided to go across the dashed line, that means I'm going through the middle between these points. And now I can either go back around the same one, or I can go around the other. Okay. So by taking some trajectory inside the unit disk, I can generate any trajectory I like on the Riemann surface. And if I resolve all of these iterations, I'll get the entire Riemann surface. Now, clearly, as you iterate further and further and further, these become narrower. And so you get into a problem of precision if you're approaching the boundary. But there's an exponential enhancement here due to this uniformizing map compared to the conformal map, which is the key to the incredible increase in precision. If I wanted to go the other way, I just go here, come back through the circle, just keep doing this. I only drew two Riemann sheets here, but I could draw. Okay, so that's the map where they've been put at -1, -1, and infinity, but you can put the three anywhere, it'll just be a sort of distorted, twisted quadrilateral. Okay? This is classical geometry and complex. Okay? It has quite an impressive consequence when applied to this problem. So I'll show you an example of that. But let me just. If you want to play with this, it's on Ovidiu's webpage. It's Mathematica notebook. You can just get used to what's happening in these maps. But just drag it with me around for a while. Yeah,
So if you apply that modular lambda function, you have some extra other singularities, not redundant. You think when you still get some branch points in your disk as well, you can eventually. Yeah.
I'll show you this. Okay, another thing that this uniformizing map does for me is that this is the generic behavior of an isolated synchrotron. At some point omega c, there's some non-analyticity, some exponent beta. Multiply it by a function which is analytic, plus a function that's analytic. The question is, how much can you learn about this? So this is a local behavior unit. So you want to know the location, the exponent, and as many terms here of the fluctuations around that exponent, because those are the fluctuations of an exponential. And you might want to know this one as well. So there's this method that we call singularity elimination, which is just better than it should be, which is that you first make a linear transformation to turn the singularity into a square root of x. This is a very well-known transformation. It's basically a fraction of the simple integral. And you can even implement it at the level of the symbol. So this is the simplest step. And why do you do that? Well, square roots are special. Square roots are special in the sense that if I then make some conformal map, such as this, the square root now turns into the square of the square root. So it becomes completely random.
So you need to know beta.
Right. And now the good thing is you can use this to find fantastic precision. So suppose you have, for some reason, a hint that maybe beta is 3/5. Well, you can go from 3/5 to a half. If you're right, you clear the singularity. If you're wrong, you won't. So you can bootstrap this, and it's incredibly precise. Like if I draw this picture here, if it were a square root, this would be a straight line. You can deviate from the index of half by 10 to the minus 10, and you can tell the difference. It's fantastically sensible. If you do not do that, or if you've got to the point where you a certain information, you also need to know the location, but that's part of the same iteration. You then might want to know what these are. Well, once it's clear, you just expand that. And the coefficients of that expansion are just related to the coefficients of that. And suppose you want this one, well, you take the original function and multiply it by the inverse of this in the reverse direction. Okay. So there's a completely systematic, elementary way to probe the local behavior near an isolated singularity to absurd precision. Once you get rid of it, suppose you get rid of this guy. Now that's the leading singularity, so you can repeat it. Eventually you run out of oomph because you don't have enough information, but you can, in principle, keep removing singularities and just probe anywhere. You don't have to probe this closest one, you can pick one and eliminate it, get the local one. Again, to show pictures are probably better than any statement of the theorem, just let me give you an example to illustrate this exponential distortion from the influence. Let's take the Borel function. This is the Borel function of the Airy function. This is the simple hypergeometric function. So it has just one branch point, one branch cut. And the the uniformizing map is a sort of big non-function. So explicitly, if you start with omega, you map to this z here in terms of these elliptic intervals k. So the expansion of omega looks like this for the inverse, so you can go back and forth. So here's a plot of, once you do this, the approximate value divided by the exact value. And this is if you just did some sort of pade, and you're probing very close to this inlet. So this should be tending to 1. Well, it's getting close to 1, but then it plummets. Okay? If you do a conformal map, then it's much, much better. So this is getting 10 to the minus 6 or something singularity. But it eventually does. The uniformizing map is perfect. And the idea of the scales here, if you use the uniformizing map, getting within 10 to the minus 40 of the actual singularity in the original plane involves going to 0.9 inside this unit test. Whereas if you made a conformal map and you wanted to get that close, you'd have to go within 10 to the minus 20 of the edge of the disk. So this is part of the reason that there's just this ridiculous improvement close to the singularities. If you wanted to just go to 0.9, so you would get very close to the singularity. It's no way from. That's part of the reason why these things are so powerful, these uniformism maps are so powerful. So for example, imagine you wanted to work out the Stokes constant to high precision. That means you want to get as close to the singularity as possible. This is very close. So you can get many, many, many digits of these Stokes constants. And suppose you want to refine your measure of the nature of this singularity. So that meta parameter, you'd also be able to get very, very close and find much higher precision. So this just, all these ratio tests and root tests are just blown out of the water, just not confident.
So this is when you know your original expansion coefficients exactly. If you know these numerically, this is go band tree.
I'll talk about that at the end. It's very interesting. That's still not completely understood. We understand some things. This is really, really important. There are some problems where we can, some problems of interest where we can.
So what is the, I mean, you were saying that it's an easy map, but what is the map when you go from beta to square root? on the previous slide.
It's a fractional derivative by the difference between the. So fractional derivative is some integral of the function divided by square root.
But you don't need to know the location of the singularity.
You can just do it at the level of the coefficients. All right, so let's apply this to that tree truncating business. So before I showed you that if you use a conformal map, you get some nice description of the whole region of the connection points. If you use this uniformizing map with the same number of input coefficients, it's just much, much better. You probably can't see it here, unfortunately, but there are some red dots and there's some black dots. The black dots are what came out of the mapping, and the red dots are what came out of the exactly the same div. And you can see what happens matching the train's asymptotics resummation as you cross this anti-Stokes lines here. But you can also do something interesting, a test. These poles asymptotically become a lattice because it's just the stress P function asymptotically. But this is a fine-tuned stress function. Remember, the stress function has a lattice of poles everywhere in the plane. But if you tune the parameters, it can become trigonometric. And you just get a line of singularities. It's not a real axis. All the others are pushed off to infinity. That's what's happening here. When you fine tune to this tree truncate, you push off in 4 of the 5 sectors these poles off to infinity. What you're left with is an almost lattice. It's not a regular lattice, but it's almost a lattice. But you can use exactly the same argument because it's a meromorphic function. You get some rules connecting the location of the pole and the second coefficient. And you can check that if you sum over all of the poles, but actually we don't have that many of them, sum over many of them, starting at one of these poles around here, you can check that these sum rules are satisfied to very, very high precision. All these nonlinear relations. It's different. If it's a regular lattice, you can just prove this much more easily. Here it's not a regular lattice. This is analogous to Eisenstein series. And you can check the connection. Yeah.
Just go back. So what we're seeing here is because again we are in the X plane, and so you took all your data from your Borel plane, and you just went back to the X plane by taking the Laplace transform. So then you have your data. But if I would have had any other method to compute the same data, get the results with the same data, wouldn't have exactly the same results here. No, sorry, but isn't that what you're doing here?
There are many ways to do this.
No, but all I'm saying is that what you're saying is just that your data is so extremely good that you get for the function at a particular, say for x is 3 for something small, and that's what you use to make the statement.
Relies on being able to extrapolate really down to some point.
No, that's fine, but I'm just, no.
Yeah, so any other method that you, so for this discussion here,
Mhm.
you just need some way to get close to somewhere around the origin with incredibly high precision.
Yeah, okay, but this is just a panel of A1, so it's also in a simple differential equation, so you could use optimal truncations at infinity and just walk down with the differential equation.
What I'm saying is that there's a key step here that better, Phil? Yes. Right, so yes, Perturbation is special. It's the reason we're studying it. Yeah, compared to, so let me show you the difficult. I'm going to go a bit into the third example. Just so there's an important problem in field theory in QCD, quantum chromodynamics. The phase diagram is theoretically very well understood. It's subject to intensity, experimental programs. It's a big mystery. So I'm not going to solve that. I will title the talk. What I'm going to solve is a model for QCD known as a chiral random metrics model, which has an interesting phase diagram. So there's temperature, chemical potential, related to density, and their coordinates. First order line, second order line, crossover line is a function. This mimics what we expect in QCD. There's an actual expression for a partition function integrating over n by n complex matrices. There's a parameter here, the mass, parameter of the chemical potential, and a parameter of the temperature, and the size of the matrix. Never mind. From that random matrix model, you can calculate physical quantities such as the pressure is related to the log of the partition. And from that, you calculate what people would measure in experiments, which are called derivatives of this pressure with respect to chemical potential. Again, you don't know what those words mean. Never mind. What you're dealing with is functions that are expansions in the chemical potential, and you want to reconstruct the actual behavior away from mu near zero. So these would be expansions generated somewhere along the zero line, but you want to get out here and probe the region. So we're dealing with an extrapolation problem. We've got an expansion here in powers of mu squared, but only a finite number of terms. And we want to know what's the best way to extrapolate that to get to other interesting regions. This is much easier than QCD because we have an actual concrete expression for the partition function. It's not an integral. Okay, so we can mimic QCD. We can just take these expansions that we can calculate from the partition function, but only take them to finite. The Pade singularities have physical meaning, so-called Liang zeros, and these play an important role in understanding what sort of phase transition is. Just look at the plots maybe for now. This is, if you take, just do Pade, we're in exactly the situation of Gerald here, and that it creates holes along there, but you want to integrate all. You want to extrapolate all. So if you just do Pade, you hit a brick wall with a whole bunch of holes that have nothing to do with the function. They're just there because that's what. If you instead make a conformal map first, this is what happens. You isolate the zeros, and you can happily extrapolate. So to put it in perspective, this is the second susceptibility, and the fourth one. If you let's see the blue, the dashed line is the exact. This is the Liang zero, so that's the radius of convergence. So the Taylor expansion just stops being useful at that point. If you do Pade, you go over this hump, go on, but then you've got these physical solutions because of these holes. And if you do a conformal map as well, then you get this blue line, which resolves this much better. Likewise, for the fourth susceptibility, the conformal map and Pade is much better if you just do you hit these physical poles, and you can't go very far beyond what you would get just from the Taylor expansion. Okay, so that's sort of interesting. But what's really interesting is that in the neighborhood of this liquid critical point, this thing lives in a universality class. It's called the 3D dissect universality class. Again, I'm going to say some buzzwords that mathematicians can ignore or state the problem just as a purely mathematics problem in a second, but there are some physicists in the case. So there's a quartic effective potential with an asymmetric term, a linear term. And near the critical point is some universal scaling in this 3D isolated system. And in the end, you can change variables to a clever set of variables, Z and omega, instead of M and these parameters R and H. And the minimization of the effective potential reduces to solving this cubic problem. When all this dust settles, the technical problem in this case would be you've got a solution to this expressed as Z as a function of omega, but you only have a finite number of terms. Okay. It's cubic. So what you have is you have information on the first dimension. You have a finite number of terms of the expansion near the origin on this first sheet, which has 2 cuts. On the second sheet, there's only 1 cut. The third sheet is just a reflection of the second sheet. So even though there are 3 sheets, there are essentially 2 sheets. Okay? So here's the question. Suppose you start with a low-order expansion on the first sheet of the solution to this cubic, in this vicinity. How far can you extrapolate that on the first sheet? But more importantly, can you go on to the next sheet? The next sheet is the low temperature behavior of the system, and the first sheet is the high temperature system. This is since it's a universal property of many statistical physics systems, even though this may look like a simple problem, just solving a cubic, this has applications in many cases. So let's see what happens. So here's my initial expansion of the solution to this cubic. So it's just been normalized to be in some nice simple form. So you truncate this expansion at some order. This corresponds to the number of terms you have in this original expansion. And you're trying to get the equation of state on, say, the next sheet, which is the relation between Z. Okay, so from studying those coefficients, you can learn that it looks like there are 2 branch cuts if you run the first sheet. You can then make this uniform as a map for that situation, which is in terms of this modular lambda function. And what you make, so here are the 2 branch points and corresponding cuts. Here are the potential lines. This is the dividing line. You can map to the upper half plane. People may be familiar with that type. But then you can map it into the unit disk. So since I've been talking about being in the unit disk, I'm going to skip it. So I've written it as a 2-step thing, but of course you can do that. Okay, so this doubly cut first sheet gets mapped into that region inside the unit disk. You can now re-expand inside the unit disk. 0 gets mapped to 0, so you re-expand around 0. And you keep the same number of times. Then you can just map back again by the index. Do it per day and then map. So this is what you find. I'm sorry, these figures are probably too small to see, but this is the real part of Z versus the real part of W, and that's the equation of state on this first sheet. And the dashed line here and the solid line is exact, and the dashed line is what you get from this uniformism starting with 10 terms. The vertical dashed lines are here. These are just the Taylor expansion of 20 terms. There's a finite radius of convergence, and you just can't go beyond just the Taylor. If you do it per day, you do much better in the neighborhood of 0, but eventually it goes down. So even on the first sheet, this uniformizing map is again completely outperforming any of its conformal maps, and it's just because it's right there. We're mapping it into a smaller and smaller region here, so whatever analysis you do inside that disk will be much more precise. But you can do this much better. You can now go to the next sheet, and I don't know of any other way to do this efficiently. So on the next sheet, there's actually one card. So this is a low temperature sheet, the next sheet. In terms of this picture, it's the little loop inside here. So it's just a reflection in that circle of all this stuff. In the unit disk case, it's that corner there that I showed before in that animation. We cross from the first sheet into the next sheet. But since after making this map, you can go anywhere you want inside the unit disk, you just do some sort of extrapolation, continuation such as it's very cheap and easy. And you can cross from the first sheet to the second sheet. And so you can go around depending which way you go, crossing onto the other sheet, or the other sheet, the reflections of one another, depending which way you choose to go. Okay? So implementing this is incredibly simple. You go polynomial, you map it under this uniformizing map, re-expand, if you didn't know the exact location of this branch point, you would soon find it. So when you do that, this is what you get. Upper curve is a blow up of the actual situation. This is the nodal points. You follow from one sheet to the next sheet to the next sheet. And here the dashed line is the uniformizing map in 20 terms, and the colored solid lines are just the exact solutions to this cubic, which you can just write in different ways, the most efficient ways in terms of symmetry. So you get, just from doing this map re-expansion, the original expansion knows the connection formula is going from sheet to sheet. So that enables you to go from an expansion on the high temperature sheet through a phase transition to expansion of the temperature sheet. Again, I don't know any other efficient ways to do that across sheets. All right, I've gone over, so skip this last example, which was effective actions. So let me just go to the conclusions. So I hope I've given you some flavor of what you can gain in terms of ultra-precise analytic continuation and extrapolations using ideas from resurgence that expansions around some regimes are related to expansion of other regimes, and the bridge between them is the Gerald transform function. And the important thing about the Gerald transform function is knowing the local behavior of the similarities. If you know the local behavior of the similarities to extreme precision, you get a better and continuation back in the region. So these conformal maps and uniform maps, what they achieve is that they enable you to go much closer to these special points than if you haven't. Once you're in that variable, you can use various techniques. I've chosen to describe them today. It's not the only technique. You just need some efficient continuation. So I only showed you two of the examples. One, we could cross the complex transitions into regions where the function has a completely different form. So trans series of one region turned into something different like another region. It's a reflection of phase transitions in systems, even in integrated model. And the main point of the chiral metrics model is a demonstration that really could cross smoothly from sheet to sheet just by going in steps. And there are many open problems. There are ways to refine this, there are ways to iterate this, and code this. There are comparisons between different types of Pade procedures. These are refinements. Honestly, I think the main idea is summarized by this idea that the closer you can get to the right variable, the better it will be, which is sort of obvious and interesting. But how dramatic the improvement is pretty simple. And second last thing is let me stop.
Maybe build upon it. So is there some kind of recipe? Say I have calculated 10 coefficients to 20 digits. It would be better to spend time calculating the next coefficient.
So it's part of it. So first of all, it should be clear to everybody that if you only know the coefficients of finite precision and you're going to start jumbling them by making transformations and doing that there, you run the risk of accumulating errors at some point. Okay? All the examples I showed you were cases where you had access to essentially infinite precision in the coefficient, which is an unrealistic thing in some applications. In some applications, it's okay, but in really hard problems like QCD, it's not. These mu squared expansions, finite precision approximations. So this is a really important question. What we actually know, it hasn't been much work on this, unfortunately, is if you have a sort of uniform finite precision. So this is not necessarily a realistic situation, but if you just say, I can only work to 10 degree precision. If you say, I have uniform noise at some strength, it is more or less the same thing. Probably a more realistic thing that should be done is to have a precision that degrades as you go up in expansion. Maybe falls off a cliff or something. It's from very good to very bad. So those things haven't been done. Let me show you what happens if it's a uniform. So imagine you've got an expansion, some coefficients, and you add some independent random variables with some strength. This is more or less equivalent to just saying, I give you the expansion coefficients and you just truncate to some. What you discover is that there's a universal relation between the number of terms you have in these Faraday procedures and the strength of the nodes. So at a certain point, you go through a phase transition as you increase n, the number of terms you have to deal with. And this is a measure of the deviation from the exact function to the noisy function. You can test this on certain classes of functions. And you see what happens is the error, the deviation, is essentially zero. It's exponentially small until you hit a certain critical n.
Just n on the
Yeah, sorry. I don't know what that is. I don't see that. Yeah, this is n on the horizontal axis. It's just like I have no idea what that thing is. It's not showing. All right. So the point is, at a certain point, things break. What does that mean? That means you start doing things like that, and you have say an actual singularity. You might be generating something like this, and all of a sudden, you just get noise. You break down and start forming a ring around the actual singularity, which has meaning in terms of that electrostatic interpretation, so you can understand what's going on. It's just sort of two-dimensional antenna. And that's, say, at the breakdown point. At that point, you're just trying to squeeze too much out of what you have using that method. What's interesting is that the point at which it breaks is universally related to the strength of the noise. So these two plots on the left and the right are using a different type of it's therefore different functions such that this parameter called Zen infimum scales differently. So you can't see very well. This point at which it breaks down is twice on the left, on the right than it is. And that's this logarithmic scaling. So you can say, if you're in a situation where this is the structure, noise is at some particular level, this is the end beyond which things break. key quantity is this thing, which is the infimum of the uniformizing map on the disk, on the unit circle, normalized by the location of the things. So for a given system, you can evaluate what it is, and that sets the relation. This is all based on the styled Zego interpretation of day and conformal maps in terms of statistics.
It'd be fair to say that then up to that point, then it's better to add more terms than to add accuracy.
Yeah. There's always the improvement according to the scale. But if the noisy coefficients at a certain point, that it's clear that it's going to break. Questions remain. This is the scaling for this situation. This can be adapted to the types of noise frequency.
So for Penley 1, first you started with like a Stokes diagram of Penley 1, and then the oral plane is mapping the Stokes onto these branch cuts. Is that true? So for Penley 1, I want to understand how you would compute, for example, like the connection constants or quantities of that form.
So start with so for the true Tonke solution,
Yeah.
Start with an expansion. You want to analytically continue that throughout the entire complex.
Yeah.
So you do this conformal map re-expansion. Now you can go anywhere in the complex. You now decide to see what does the function do along this. Then you can check it against the connection.
So where are the Stokes lines when you take all these maps?
You discover them by plotting. I mean, if you know the equation, you know what I'm saying is you can discover them just from the expansion. If you do this extrapolation, you see that there is a relation between the 1 and 2. So it's built in to this expansion.
Oh, so you're starting with just nothing apart from just the asymptotic expansion, and then you're reconstructing all
That's
the.
the point.
I see. Okay.
And the only reason for doing Penley 1 is that we know what has to happen, what should happen. Whereas if we pick some other random equation, if we get something, but how do you know?
Yeah. What if you do a conformal map after the information?
Well, at a certain point, you just run out of
Okay.
references.
Okay.
And there's no point because you're already in the right variables.
Yeah.
But one issue I wanted to get across is that it's very rare that you will know the exact. It's also very common that the leading singularities 1, 2, or 3, in which case those are completely known, and just using those is a dramatic improvement. And if you do the singularity elimination, you can just pick off singularities 1 up to the point, and just you don't even need them.
But for the cases of Penley, for example, don't you know the uniformization map just from the underlying geometry?
Something. The fact that you have all these parallel singularities repeated.
Yeah.
It's not obvious what the uniform map. We found that the uniform map is. But you didn't need that to really get certain precision. Just based on readings.
Just to comment on the noisy case, I don't think the deeper reason for it is the accumulation of all those operations. The deeper reason is that you're solving a quotient problem for the elliptic equation, the analytic continuation is only the real number, the Riemann equations, which are elliptic. So in the high frequency modes, you're inherently unstable. So there is always a relation between the noise level and the nodes where you have a cutoff in order to go that far. So this is a completely typical behavior for elliptic Cauchy problems.
Adapt that to different.
Yeah, right. So depending on the depth of continuation, so to speak, you have a different level between different cutoff relation between the noise level and the number of expansion coefficients or frequencies, so to speak. In model cases, there are clear relations, and otherwise, you are just observing them experimentally.
So actually, this was an experimental observation, but then we derived it from problems.
It's connected to the other model closeness of solving Cauchy problems for elliptic systems.
Questions online, maybe?
Sorry.
Questions online, maybe?
Oh, yeah.
Yes, sir.
Anybody have any questions online?
No more questions online,
Other reviews?
but I think they can write. No, but I think
Oh,
also
there's-
the previous.
Yes, the Gerald ones.
So,
Technical questions.
technical questions. Okay. Well, thank you, Gerald.